8.3 Rotational Dynamics. In this subtopic 8.3, we have two learning outcomes. First is define and use moment of inertia, and second, state and use torque. Okay, the first one, moment of inertia. Okay, inertia, recall back, inertia is the tendency of an object to resist any attempt to change its velocity from rest or from linear motion. So for moment of inertia is the tendency of an object to resist any attempt to change its angular velocity. Now, moment of inertia is related with rotational, so it is resisting attempt to change angular velocity. So this figure shows a rigid body rotates about a fixed axis. Now, moment of inertia is defined as the sum of products of the mass of each particle and the square of its respective distance. So, mass of each particle, we have mass 1, mass 2, mass 3, and so on. Where mass 1, you have R1, R2, R3, and so on. So, moment of inertia is defined as the sum of mass and square of its respective distance. So, moment of inertia, you have mass times with square of distance, R1 squared plus M2 R2 squared plus M3 R3 squared, and so on, where we have basically MI R1 Ri squared. I is moment of inertia, M is mass of particle, and R is the distance from particle to the rotation axis. On one object, you have a number of particles. Moment of inertia is a scalar quantity where it is analogous to the mass in linear kinematics. So, when you have S displacement with angular displacement theta, now for inertia, in linear you have mass, in rotational we have moment of inertia. Unit for moment of inertia is kg m squared, comes from mass times r squared. Mass is kg, r is m squared. Factors that affect moment of inertia is mass of body, shape of the body, and the position of the rotation axis. Mass, shape, and position from rotation axis. So this table shows a various shape and what is the equation for moment of inertia. First example is hoop or ring. Hoop or ring are also called as thin cylindrical shell. So to calculate the moment of inertia of this object, we're going to use mr squared. For a solid cylinder, the moment of inertia is half mr squared. So the tendency to rotate is half from ring, which means ring is easier. Ring have higher tendency to resist change compared with solid cylinder or disc. Okay, different shapes given. Uniform rod or long thin rod, where the axis through the center of mass. The moment of inertia is 1 over 12 m times with the length squared. Solid sphere is 2 over 5 mr squared, but a hollow sphere is 2 over 3 mr squared. Different shape, different position of axis of rotation will give you different equation for moment of inertia. Relationship between torque and angular acceleration. So this figure, when you have mass and r and you applied force, shows force acts on a rigid body cause it to rotate. So, how to calculate our torque? Force is equals to ma. Force 1 equals to mass 1 times with A1. And based on previous subtopic, A, you can relate with the rotational, use A equals to R alpha. Now, when you change your A into alpha, it will be M R alpha. Okay, formula for torque is RF sine theta. Now, when we combine torque with force, so torque RF sine theta, here we will have R Then our F is M1 R1 alpha 1 sine theta. Now because it's 90 degrees, sine 90 is equals to 1. Now you will have M1 R1 squared alpha. Mr squared is moment of inertia. So from here, you can have mr squared is moment of inertia, which will give you formula of torque equals to I alpha, which means torque, you have two formula. Either you have F r sine theta, and one more formula for torque is I alpha. From the equation, the net torque acting on the rigid body is proportional to the body's angular acceleration. Your torque is directly proportional with alpha. Now, torque I alpha, this is rotational, where it is analogous to the net force, where you have your F equals to ma. So torque related with force, I related with mass, and alpha related with your linear acceleration. Okay, that is basically 8.3. Again, all the calculations will be done in your tutorial. 8.4 Conservation of angular momentum. Define angular momentum and state principle of conservation of angular momentum. Angular momentum, the symbol is L. Angular momentum is defined as the product of angular velocity and its moment of inertia. We can relate with general formula of momentum, linear, P equals to mv. So, for angular momentum, we will have P equals to mv. So, we will have angular momentum, okay, as previous, m relate with I, and v is our omega. So from here, we will have angular momentum equals to I omega, where L is angular momentum, I is moment of inertia, and omega is the angular velocity of a body. Word angular means it's involved rotation. Linear is momentum P, rotational momentum, which is angular momentum, is L. It is a vector quantity and the unit is the same with momentum, kgm squared as -1. Principle of angular momentum. Before this, we have principle of conservation of momentum. Total of P initial equals to total of P final in a closed system. So here, in a closed system, total angular momentum is constant or conserved, where we have total of angular momentum initial equals to total of momentum final. In case of total of angular momentum formula, I omega initial equals to I omega final. So constant. This is a rotational punya case. So you can watch more, you can watch examples from this YouTube link, or you can go through your lecture notes to understand more on principle of conservation of angular momentum. Okay, so that's all for chapter 8. Thank you.